Welcome back to AP Stats, where I'm still not affiliated with the College Board. My name is Dr. Kling, and we're on to the topic of the normal distribution. And before I inflict my drawing of the bell curve on you, you can imagine how bad that is. Let's look at some other people's drawings of the bell curve. This one might be a particularly good one to look at because it gives you the percentages that fall within various standard deviations. So if you look between, no, pop up again. There you go. If you look between -1 and 1 standard deviation, for example, you get 68% of the probability for a normal distribution. So 68% of scores will fall within that interval. And then you add another 13.6% between -1 and -2 standard deviations, another 13.6 between 1 and 2. There's these well-known, well-calculated relationships. Okay, so back to me. So you'll often see people say, or hear people say that there are lots of things that are normally distributed. So height, men's height, women's height, normally distributed. Birth weight of babies, normally distributed. IQ, normally distributed. Stock market returns, normally distributed. So you'll hear all that. And I'm going to argue that none of these are in fact normally distributed. They are approximately normally distributed. Approximately normally distributed, but not exactly. And what I want to emphasize, in fact, before I even draw it, I want to emphasize that approximately that for extreme values, that the normal distribution either overestimates or underestimates the probability. And for example, one thing that you can use as a normal approximation is total monthly rainfall in October in the Washington, D.C. area, where I think the mean is about 3 inches. And you can use, and I am not sure what the standard deviation is, well, let's say it's 1 inch, I'm not sure. So you could use a normal approximation to, and it would work pretty well for most of these. For when the normal approximation works well, it works well from about -2.5 to +2.5 standard deviations. Once you get outside of that, my claim is it doesn't work well. For one thing, the normal distribution says there's some probability of, even though it's very small, at -infinity and infinity. So if you were to use the normal approximation and I were to say, I'll bet $1 million to 1,000 that rainfall will not be negative this October. We will not have negative rainfall this October. Well, I think if you had any sense at all, you would not make this bet, because you wouldn't want to give me $1,000 when we find out that the rainfall is not negative. But if you were to use the normal approximation, you might very well decide that this is a good bet. So the moral of the story is the normal approximation doesn't apply, and there are a lot of things where it's just physically impossible for it to be negative, and therefore right away we know that there's a range of values where the normal distribution cannot apply, because the normal distribution would allow negative values. Or let's say we're talking about the birth weight of babies, and with the normal approximation, you cannot rule out a 50-pound baby. You cannot rule out a negative 1-pound baby. Okay, but we know we're not going to observe these, so that is wrong. So that's a case where the normal sort of overestimates the probability of an unlikely event. It can also underestimate the probability of an unlikely event. In the financial crisis, a guy from Goldman Sachs famously complained that we're seeing 100-year events every 2 years. What he was saying is that events that, according to the normal distribution, would only occur every 100 years were occurring every 2 years. And again, that's because the normal approximation is not a good approximation for extreme events. And in the case of financial events, it greatly underestimated the probability of extreme events. That extreme events really were much more likely to occur than what the normal distribution said. So his error was assuming that there was a normal distribution. So that's my little lesson on the applying the normal distribution and being very careful not to apply it out in the extremes. And now, just for the fun of it, let me draw it, so we'll see how bad I am at drawing it. It's never really supposed to touch the axis. You can see how bad I am at it. Anyway, and what I've been saying is, let's say that this is about 2 standard deviations, and this is about one standard deviation. It's about 2. That once we get out much past 3 standard deviations, so we'll put the 3 here, or once we're in the neighborhood of 3 standard deviations or more, out here we're not getting a good approximation. In here, even though in here we often are getting a good approximation. So we do get a good approximation in here, but we almost never get a good approximation out here or out here. And that's the moral of the story. Next time we'll talk about how to go from natural units to percentiles using the normal distribution.